How was the exam? How was the exam? Tough? He says it was not tough. You will only have problem in selecting the questions or something. Anyway, hope okay. So today we want to discuss another topological property of metric spaces. Okay. So I actually wanted to do it before midterm, but somehow I could do due to my personal reason. So it's called connectivity, connectedness. Connectedness. So some sort of connectedness. It's like an interval is connected, as you know. But it's a topological property. In the definition we make, the objects need not be metric spaces. You can assume it's general topological spaces. It holds for, I mean, the definition or the proof mostly holds for general topological spaces. But if you are inconvenient, you can assume that there are metric spaces. Okay. So the definition, you can assume X is any topological space, but we are taking X is a metric space. Then there is no difference. Okay. Because we are going to use only open sets, which are, the notion is, I mean, the notion is more general in a topology, it holds in topological space also. So X is a metric space. X is said to be connected if there does not exist, this, by this I mean there does not exist. There does not exist open sets. Maybe I'll write non-empty proper open sets, that is non-empty UV, where U and V are not equal to X, not empty. Non-empty proper open sets, non-empty proper disjoint open sets. Okay. Disjoint open sets UV such that X equal to U union V. This is union. That X can be written as disjoint union of U and V, where both U and V are open, and they are not. I mean, they should be proper. They should not be. One should not be empty. Other should not be X. I mean, that's always holds. Okay. So this is the definition of connectedness. It's clear. So these are called. If you can write it like that, these are called connected components. I mean, if that is connected, because that may not be connected. Suppose if you can write it like that, this is one component, this is another component. If that is connected, they are called connected component. Otherwise, I mean, it can be completely disconnected also. We'll make the definition. So if it is not connected, if it can be written like that, then we call it disconnected also. So this is equivalent to, that is, I mean, this definition is equivalent to saying, if X is equal to U union V with U intersection V equal to empty, then either U equal to X or V equal to X or U equal to empty set. One of this should hold. Okay. I mean, if it can be written like this, then it should be, one of them should be the whole set, the other one should be the empty set. So this is the definition of connectedness. So this definition, one can easily see, this definition is equivalent to saying the only subset of X which are both open and closed. This is equivalent to this. If this holds, then I mean, it's equivalent to the definition of connectedness, which are both open and closed, are X and empty set. Okay. That's clear. If something is both open, I mean, if it can be written like that, then there will exist proper open set which are both open and closed. This U, I mean, if it can be written as X, can be written as U union V, where U intersection V is empty, they are disjoint, then this is both open and closed because the complement is open and it's clear. So this definition is clear. And examples, I mean, we will get more examples. For example, the fundamental example is an interval is connected. For that, we need a proof. So, I mean, I'll proof later. One is any interval in R. Proof later. I mean, it will follow that. Proof later. So, is connected. Okay. This is an example. But non-example is you can take two disjoint interval. I mean, any interval means it can be open, it can be closed, it can be half open, half closed, anything. Okay, anything is connected. You can take this kind of interval, half, 1, union, 3, 4, whatever. Doesn't matter. This is not connected. Okay? Of course, in the relate, I forgot to say. So this is for general X. So this is any subset is connected if it is connected in the relative topology. If it is connected, maybe I'll write it there. Okay, this example will come later. I erase it. If it is connected in the relative topology. In the relative topology or the restricted metric, you can restrict the metric to the subspace that will generate a topology, that will generate new open set. Okay, if it is connected in the relative metric or relative topology. Okay. You know how the topology looks like. If U is an open set, I mean, any for, we have seen this, for any S contained in X, so A contained in S is open in the relative topology if and only if there exists a U contained in X open and U intersection S is equal to A. We have seen that. Okay, it should be intersection of open sets with S. They are all that is a relative topology. You can directly define relative topology like that. Or when the matrix is restricted to S, that will give this topology. These are all the open sets. Okay. So we say, I mean, if we say some subset is connected, if it is connected in the relative topology. So that definition is there. So with respect to that definition, this is open here. Okay, this is an intersection of some open set. We can take the intersection half minus epsilon 1. If you take the intersection of this set, you will get this. Okay. So this is open, this is open. So this is union of open sets. So non-trivial open sets. So this is not connected. And similarly, if you take R, I mean the same example, R minus 0 is not connected. This is just the negative real numbers, union is positive real numbers, strictly negative, strictly positive. So they are all open. So this is also not connected. On the other hand, this is connected. Of course, proof later. Okay. You'll see the proof later. Of course, the fundamental example is interval. So for that, we need to prove. Okay. So you wait for the proof. So another definition I want to make, yeah. I minus I, what is I? Finite set, countable set will also, countable, R and any countable set, yeah, you can avoid countable set and then you can take care. Yeah. Yeah. So I forgot to say, yeah, n greater than R. Yeah. Yeah. We will use, I mean, there is no point in saying we will work with the proof later. Okay. We'll prove this and we'll see the proof. So definition, this is another definition. We want another extreme case when compared to the connectedness. This is something called a subset A contained in X is said to be totally disconnected. Of course, if it is not connected, then we call it disconnected. We can call it disconnected. Something is totally disconnected. There is no connected component or something. So if for any X and Y in A, and X is not equal to A, of course, there exists open Ux, Uy. Okay. I mean, maybe in X or, I mean, it doesn't matter. Maybe in X open. Or you take the intersection with A, that will satisfy, then that will be equality in the definition. Okay. Ux, Uy open, such that X is in Ux, Y is in Uy, and A is contained in Ux union Uy. Any X and Y, this should happen. It is not just disconnected, it's something more than that. Okay. Any 2 points, then you can have open sets around them, separate them by open set, and their union is everything. I mean, this union covers the whole thing. So examples of totally disconnected sets is, for example, rationals. I mean, if you take two rationals, R1, R2 in Q, R1 not equal to R2, then there exists a X in the interval R1, R2, irrational. And X is intersection R minus Q. Okay. This is irrational. If there exists a X, then this minus infinity X equal to Ux, and what do you want to do? Minus infinity X, right? Minus infinity. I mean, assume R1 is less than R2. Okay. And X infinity. Okay. This is Uy. This is R1. This is UR2. Then then their union, of course, will contain. I mean, it will only leave X in their union, which is irrational. It doesn't matter. So Q is contained in UR1 union UR2, of course. Okay. So rationals are completely disconnected, totally disconnected. Another set, we will see the example later, proof later, even the definition later, something called counter set later. The nice thing about this is a closed set. Okay. So a closed set, it's difficult to construct closed set which is totally disconnected. And this is a closed set also. So we will see this example possibly in the next class. So this is totally an example of a totally disconnected set. Okay, so now let us come to the first example, so which we make it as a proposition. J contained in R is connected if and only if J is an interval. By interval, I mean open or closed or half open, half closed, whatever. Half open, doesn't matter. So all these things are connected. Proof. First, we prove the other way, which is easier. If it is connected, then it is an interval, which is easier. So if some set S contained in R is connected, and if it is not an interval, we want to prove that. I mean, let's not even do that. Let's say S is something contained in R. If it is not an interval, then we say that it's not connected. Okay. So if and S is not an interval. That is there exists A, B there exists A less than C less than B, okay, such that A and B are in S, okay, and C is not in S. Okay, that is, if it is not an interval, that's the definition of interval. A and B are there, then anything between A, B should be there. That's the definition of interval. This is the negation of the, it's not being not an interval is this. Definition of not an interval is this. A and B are in S, but there is some C between A and B which is not in S. Okay, this is the definition of not an interval. So then we want to get a contradiction. Then we want to prove it's not connected. Okay, that's what we want to prove. Okay. So suppose, so it's not connected. So let U equal to the same thing, minus infinity C, and V equal to P infinity. Okay, these are of course open. They are open. Okay, and of course, I mean U intersection S union V intersection S equal to S, of course, because C is not in S, and they are open in the relative topology, so it's clear. Okay, these two are open in the relative. These are open in R. These are open in S. These two. These two are open in S. Okay, in the relative metric, and their union equal to S, because C is not in. C is not there. Okay. So one way is clear. If it is not an interval, then it is not it's not connected. So if it is connected, it has to be an interval. So now we want to prove that any interval is connected. Okay. So to prove the other way, so suppose J contained in R is an interval. Then we want to prove it's connected. And J is equal to, and there exists, suppose there exists U, V contained in R open, and J is equal to U intersection J union U V intersection J. Okay. Suppose we have open sets U and V such that this happens, J equal to this. That's the, then we have to prove that this is either equal to whole of J or this is either equal to whole of J. One of them should be empty. That's what we want to do. Okay. Suppose the other way, suppose U intersection J and V intersection J both non-empty. Okay, they are both non-empty. And let's assume J equal to, let I write J equal to AB. I mean, it doesn't matter. AB or AB or AB or AB, okay, whatever, doesn't matter. It is just the endpoints are A and B, whether it is closed or doesn't matter. Okay. Okay. Suppose this is the case, then both are non-empty. Then there exists a C in U intersection J and D in B intersection J. That's all. That's what it means. It is non-empty. And assume, of course, one of them should be less than the other. We assume the C is less than D. Otherwise, you interchange the opens. Okay, C is less than D. Okay. Okay. So we want to finally show that one of them is empty. Otherwise, there is a contradiction. That's what we want to do. Okay. So since C is in U intersection J and this is open, supposed to be open in the relative topology. Okay. So there exists the epsilon greater than 0 such that C plus epsilon is contained in U intersection J. Yeah, because we are assuming it's an interval. Okay. Right? I mean, because if there exists an epsilon such that C, there is a neighborhood around C which is contained in U, and the C is in the middle, so there exists a neighborhood around C which is contained in J also. You assume C is the interior point, okay? Right? Not the end point. So this is true. So let x naught equal to supremum of all those x such that Cx is contained in U intersection J. And this is non-empty because there is a C plus epsilon. There is one element in the set. This is non-empty. This is not equal to empty. Okay, and the supremum exists. Okay. And x naught is something, it's about the interval. So x naught is strictly greater than C. Okay. And x naught is less than or equal to B because everything is contained in the interval, right? Because we are dealing with the interval. Our J is an interval. Okay. Is okay. So x naught is less than B. So first case is, let's assume, and we want to prove that this x naught is actually equal to B. Okay. Now suppose x naught is strictly less than B, it is not equal to B, strictly less than B, then, okay, then we want to consider cases. Whether x naught is in U, x naught is in I intersection, J intersection U. If it is in J intersection U, if x naught is in J intersection U, then there exists epsilon greater than 0 such that x naught plus epsilon is contained in J intersection U. But that will imply that x naught plus epsilon will, I mean, up to x naught is there, and this closed interval, this union is also there. This implies this is a contradiction to that fact, right? Not possible by definition. Is that clear? The reasoning? If x naught is here, because it's open, okay, and this is an interval, this is an open. Okay, there is x naught plus epsilon is in J intersection U. Okay, that will mean that C x naught plus epsilon is contained in J intersection U, because already J up to this x naught is there. Okay, any point before that. So because of that, this will be there. So the x naught cannot be that supreme. Okay, so because of that, this is not possible by definition of x naught. So x naught is not in that. So now suppose x naught is in J intersection V. Okay. Then because again this is open and this is an interval. Okay, I mean this is an intermediate point. X naught minus epsilon x naught. Okay. This is contained in there exists epsilon. Okay. This is contained in J intersection V. Okay. This implies there is a point between x naught and x naught minus epsilon, which is in J intersection V, which is also in J intersection U. This is not possible because they are disjoint. Not possible. Since U intersection V is empty. This is not possible. X naught minus epsilon, x naught. So there is a point between x naught minus epsilon and x naught, okay, which is in J intersection V. But the x naught is the supremum of such things. So that point will be in U intersection J also, but they are disjoint. So this is not possible. So this assumption is not possible. Okay. So this implies that x naught should be equal to B. Okay. If you have a problem, you ask me. Okay. There is really nothing. So x naught equal to B. Now we have to show that this leads to a contradiction. The first thing is if x naught equal to B, and I mean B is the supremum. So suppose x naught is in, if x naught is in u intersection v intersection I, let us see v intersection I, okay. Then again the same thing. Then there exists epsilon greater than 0 such that x naught minus epsilon b is contained in v intersection j. So this is j. Okay. Again, this is not possible. Okay. So this is not possible. Okay. So x naught is in I intersection u. That is that it starts with C, no? C, B, C, B, whatever, up to here. B is completely contained in I intersection U. Okay. Or if it is the, I mean, if it is the whole open interval, it is up to the end point. I mean, let me not, it depends on, if it is open interval, it is up to CB. If it is closed, if it includes B, then it has the left hand, I mean, the right extreme also, the B also. It depends on that. I have to write all that. Okay. So it is just starting from C up to B. It contains everything in this I intersection U. But then our C prime is supposed to be something which is not there. C prime is greater than this. C prime is supposed to lie here. This implies C prime is in I intersection U. Everything greater than C, which is in that, should be here. But our C prime is greater than C, so it has to be somewhere here. If it includes B, or I mean, that depends on that whether it is. Okay. So C prime is in I, C or D. Sorry, D. What I call as D. D is the other one. The D is greater than this, and the D has to be in I intersection B. Okay, but we have assumed D is in I intersection B. This is also a contradiction. Okay. This is also a contradiction. So it's proved. Okay, none of them is possible. So all connected subsets of real line are intervals. Now let us prove a nice criterion, which is very easy to prove, which is very easy to see, but it will be very useful. So proposition. As I said, all these things are true for general topological space. There is nothing specific about metric space. Okay. X is connected if and only if, this is if and only if f from X to this plus or minus 1, this set, okay, with discrete topology. Discrete topology, or you take the induced topology from real line, which is discrete topology. Discrete topology is continuous, implies f is constant. Okay. The only continuous function from that space X to plus or minus 1 is constant function. It has to be 1 everywhere, or it has to be minus 1 everywhere. It cannot take both the values, 1 and minus 1. And it is clear. Proof. Okay, X is connected. Okay. And if f is a function from X to plus or minus 1, okay, plus or minus 1, then f in u equal to f inverse 1, v equal to f inverse minus 1. Then of course, this is everything. It has to take either plus or minus 1. So X is equal to u union v. Okay, and they are disjoint, of course. U intersection v is empty. Okay, then by connectedness, either u has to be empty or v has to be empty. That means by connectedness, By connectedness, either u equal to empty or b equal to empty, which means this implies f is constant. It's clear. On the other hand, suppose, so this is this way, suppose all continuous function on f from x to plus or minus 1. I mean, suppose the only continuous functions are constant function. So that's what I want to make. Suppose the only continuous function. No, let's prove the other way. Let's prove that if this does not happen, that does not happen. Okay? No, we proved that x is connected implies this. Okay, not connected implies not this. Let's prove that. So suppose f is not connected, that is easier. Suppose f is not connected, then there exists u v open such that u intersection v equal to empty, and x is equal to u union v, and both, I mean, the u and v are proper. U contained in but not equal to x. V is also contained in not equal. They are non-empty also. Okay. All this. Now you define f of f restricted to u equal to 1 and f restricted to, you define on u it is 1 and f restricted to v is minus 1. Okay. And it is certainly continuous. There are only two open sets in this discrete metric space, and they are continuous. F is continuous. Okay. Inverse image of plus 1 is this, inverse image of minus 1 is that, and it's continuous. Okay. F is continuous and it's not constant. Okay. Because they are proper open sets, F is not constant. And so this is a nice, it's very easy, but it's a nice criterion. So this is fine. Now let us prove the other proposition, which says that this is actually a topological property. Connectedness is a topological property, which is preserved under continuous function. Okay? I mean, which is preserved under homeomorphism, in particular about continuous with respect to continuous functions. Okay. So x is connected, and f is from x to y. Y is another topological space. Okay. Then continuous. It has to be continuous, of course. Then f of x is also connected. Use this criterion to prove this. You can prove it directly also, and this is just easier. So we want f x is connected. We want to prove that f of x is also connected. So proof. So let g be a function from f of x to plus or minus 1. Plus or minus 1. Then g composed with f is a function, continuous function, continuous function to plus or minus 1. You don't see when you invoke this criterion, then it's you don't have to use any open sets or something. You will follow immediately. This is a continuous function. So since x is connected, g of f is constant. Okay. G of f on x is constant, on f of x, g has to be constant, right? If not, what does it mean? If it is not constant, means that x is f of x1, f of x2, that g of f of x1, g of x2 are different. That means g of f is not constant, right? You just write the definition, it follows. So this implies g is constant on f of x. Okay, we are not talking about y. Okay, we are only talking about f of x, the range only, range of f. If it is on to, of course, y is also connected. Okay? So the proof is over. Okay, direct. Okay. So when you have these two things, then the theorem which you know already, maybe you might have seen the proof. The intermediate value theorem follows immediately. That is, if f is a continuous function from some interval ab to r, okay? Suppose continuous. Okay? An interval is continuous, so f of ab is also, I mean, interval is connected, so f of the interval is also connected when f is continuous. Suppose y is between f of b and greater than f of a, or the other way, doesn't matter. I mean, if their order is reversed, then it will be, it is just between them. Okay, f of a, f of a, f of b. Then there exists a x in ab, the interval ab, such that f of x equal to y. Okay, that is just clear. I don't have to write the proof. AB is an interval which is connected. We have proved that f is continuous. So f of that interval is connected, okay, which is going to be that connected means it's again going to be interval. So which is just going to be f of a, f of b. So y is between f of a and f of b. So I mean every value should be taken from the f of a to f of b. Okay, maybe many times, it doesn't matter. Okay, but the image is going to be all the values. So there should exist some x such that this happens. So this is clear. Okay. And this intermediate value theorem is of course very important. Without that, I don't see how you can say that there exists the nth square root of something, some real number. Okay. So, and there are many theorems which you can prove. For example, this is the application. This is the proposition. For example, I mean, there exists a unique nth square root for any x in R. There exists unique x in R for any y in R, maybe 0 infinity, sorry, 0 infinity. There exists a unique, I mean, this unique is for positive only, unique x in 0 infinity, such that x power n equal to y. Given any y, you can find a nth square root, nth root. Okay, proof. I mean, choose some n power n. I mean, you can choose n greater than y, so n power n will be greater than y also. Okay, and you take f of 0. So f is a function from 0 to n power n, or I mean 0 to infinity to 0 to infinity, which is the exponent x power n, which is of course continuous. It follows from the basic. X is continuous. You multiply n times, that's also continuous, of course. Okay, so but the nth square root, for that we need this. Okay, so then it takes the value. I mean, so if you take this interval n power n is going to 0 n power n. Okay, where you have the y in between them. So there exists a unique something which takes the value here. So so there are many things you can prove using intermediate value theorem. So next proposition is, if you have two, of course, union of two connected set need not be connected. You can take one connected set disjoint from another connected set, and if you take the union, it need not be connected. But if two connected sets intersects, then their union is connected. Okay? So X be any metric space. X is just a metric space or a topological space. And if you have one, if A, B, contained in X are connected, then and A intersection and A, they are intersecting. A intersection B is non-empty. Okay? If it is empty, we cannot say, then A union B is also connected. I mean, so actually the theorem is the following. So if AI is a collection of connected subsets or connected subsets of X such that AI intersection AJ is non-empty for all IN. Then they are mutually intersecting. If you take any two, they are intersecting. Then union of AI is connected. All these things will follow if you invoke that proposition. The third one is A contained in X is connected, and B is something which is contained in A closure, and it contains A. Okay? I mean, it can be equal to, we want to prove that closure of a connected set is connected, but we prove something stronger. Some B may not be equal to closure, but it contains A and it's contained in the closure. Something bigger than A, but it's still contained in the closure. Okay? Then B is connected. The proofs are very easy. It is only, I mean, it should be left as exercise. But since we don't have anything really difficult, I'm doing all these things. There is not much deep theorems are here. Okay? And the fourth one is X, Y are connected metric spaces. Okay? Connected. Then you can take any, I mean, you know, the topological is just, I mean, topology generated by U cross V. I mean, if you have a topological space X, topological space Y, then you take all those sets of the form U cross V inside this, take finite union and arbitrary, finite intersection and arbitrary union. Okay, that will give it, that will be the topology on this. But we don't have to worry. You take a metric here, you take a metric here, then you take any of those metric, 2 metric or 3 metric, or I mean, whatever, the Q metric or 1 metric or the maximum infinity metric, anything you take. Okay. Then X cross Y is connected. Okay. It is just, I mean, for us, the topology here is if something converges here, some sequence converges here. I mean, we are not using, I mean, if it is metric space, if it is topological space, we have to use net. But since we haven't defined net. So if you have a sequence here which converges, means it should converge coordinate wise. That's all. Okay? That determines, so if you determine the convergence, then determines the topology. So that's all. Proof one by one. We actually proved this. I mean, but let me tell you the proof here and then this proof. So A union, you want to prove that A union B is connected, given A and B are connected. Okay. So suppose F is a function from A union B to plus or minus 1. Okay. Then you want to prove it is constant. F restricted to A is constant. Okay. And F restricted to A for any X, that should be same as something in the intersection. Okay. Some X is in the intersection. Okay. And that should be same as F restricted to B is also constant. So if X is in the A intersection B, and that should be equal to F of X for both of them. So it's clear. F is actually constant. Let us prove the other one. Let us write the proof for the other one. F is something between union AI 2 plus or minus 1. Okay. Then let X is in AI intersection AJ. X is in, yeah, and X is in AI and Y is in AJ. Okay. Xi is in AJ and Xj is in, Xi is in AI, Xj is in AJ. Okay. Then F restricted to AI is constant. Okay. This implies F of Xi is equal to f of x naught. F restricted to aj is constant. This implies f of xj equal to f of x naught. Okay, so this implies f of xi equal to f of xj. If you take any xj, xj, then this is true. So this implies that, I mean, ij are arbitrary here. So f is constant. This means the union is connected. Okay. We just use this criterion again and again. I mean, if you directly use open set and other things, it's unnecessarily messy. Okay? This is direct. There is really nothing. Okay? The second one. The third one. So if A is connected and B contains A and contained in A closure, we want to prove B is connected. So F from B to plus or minus 1, something. Okay. And F restricted to A is constant. Okay. And it's clear. Now, if you have a B in B, there exists a AN contained in A such that AN converges to B because B is in the A closure. Okay. Now, F of AN is constant. Okay. And is equal to C. And F of B is also equal to C. So F is constant. Right? I'm unnecessarily writing all that. So this implies F is constant. And this means B is connected. So in particular, A is connected, then its closure is also connected. Or anything which contains in the closure is connected. Anything which contains A and a connected set may have disconnected subsets. Okay? But if something contains A and contains in the closure, then it is connected. Then A closure is connected in particular. So the final one is the product. That's one. So we have XY connected spaces. Okay. And we want to prove the cross product is connected. X cross Y is connected. Now F is a function from X cross Y to plus or minus 1. We want to prove that F is, which is continuous, of course. We want to prove that this is constant. That's what we want to prove by considering the restriction, of course. So what we do is the following. So you can, just for our understanding, this is X, okay, and this is your Y. Okay? It need not be real, right? Just for your understanding how it goes. Because we are anyway going to write this. Now you want to prove that this is, you take a point here, this is X0, Y0. You take a point here, XY. You want to prove that F of this XY is equal to F of X0, Y0. That's what you want to prove. So you go like this and like this. And this point is, the X0 is same, no? X0, Y. Okay. So you prove that F of X0, Y0 is same as F of X0, Y, which is same as this. Okay. That is because, so what is this line? This whole line, what is this line? This is just going to be, yeah. So since, there is no restriction, this is what is called embedding. So since Y is connected, okay, this one is connected, X0 cross Y is connected, right? Because this map, the map is Y going to X0, Y. That is a map, is continuous, right? If Yn converges to Y, then X0, Yn will converge to X0, Y. Okay? So this map is continuous because of the continuous. So we are using several facts. This map is continuous. Continuous image of connected set is connected. So because of that, this x naught, this singleton cross y, this is a copy of y, of course. So is connected. So this line, whatever we have written as a line, is connected. So so this implies f restricted to x naught cross x is constant, because restriction is of course a continuous function. Okay, so this implies is constant. So because this is connected, this is constant. So this implies f of x naught y is equal to f of x naught y naught. Okay, for all y. Okay. On the other hand, you consider this. This is going to be this y is fixed here. Okay, this is not a varying y. Okay, now this x cross the singleton y is also connected for fixed y, of course. For some fixed y, this is also connected because x is connected. This is a continuous image of x. Okay, so this is connected. Okay, so this just means f restricted to this is constant. Okay, so this implies f of xy is same as f of x naught y. Is constant. Okay, this implies f at x y is same as f of x naught y, which we have already proved that is equal to x naught y naught. Okay, so it's done. Okay. So we have proved that the cross product of two connected spaces is connected. Okay, this is for general topological space. We haven't used anything about metric. Okay. So let me pass. If you have any doubt or anything you want to go through again, I assume everything is clear, crystal clear. Okay. So now, I mean, I haven't given many examples of connectedness because I want to introduce a stronger property which will imply connectedness, and most of our objects will be path connected. That's what I want to introduce. So this is the definition. So X is some metric space or a topological space. X will have, and if we have 2 points x, y in X, okay, then a path is a continuous map. Is a continuous gamma from the interval 0, 1 to X. I mean, the path between and x naught, x can be equal to y, doesn't matter. Okay, then also there is a path. The constant function will be the path. Okay, yeah, path between x and y, xy, is a continuous function. Is a continuous gamma from 0, 1 to x, such that gamma of 0 equal to x, gamma of 1 equal to y. That's all. Okay. And we say 2 points in x are path connected, and it's important. So if it, I mean, we may consider some s's, s may be a subset, then its a path should be completely inside s. There is nothing outside x. Okay. I mean, so if s is contained in x, then a path and xy are in s. Okay, a path in s, okay, between x and y is a continuous map gamma from 0, 1 to x. It should be completely contained in the image should be completely contained in s. Okay, such that gamma of 0 equal to x, the gamma of the 1 should be equal to y. The end point should be x and y. Okay. So we say X and Y are, we say X, Y are path connected if there exists a path. Okay? If there exists a path between them, between X and Y. So this is clear. Let me write it clear. Path connectedness is an equivalence, path connected between X and Y. I'm not talking about the set. Okay? So path connectedness between elements X and Y is an equivalence relation. Clearly, X is path connected to X. You take the constant function. Okay? And constant function gamma X is equivalent to X. You take gamma from 0, 1 to X. You give gamma of every t equal to X itself. Okay? 1. The reflexivity is clear that if X is connected to Y, X is path connected to Y, that is there exists a gamma from 0, 1 to X with the gamma of 0 equal to X, gamma of 1 equal to Y. Okay? Then you take gamma prime to be gamma of 1 minus t. That will give you a path between Y and X. Okay? So the third one, if gamma is a path between X and Y, connect X and Y, and gamma prime is a path between Y and Z. Okay? Maybe gamma 1 is a path from there, gamma 2 is a path from Y and Z. Then you define gamma from 0, 1 to X by gamma of t equal to gamma 1 of 2t. If, no, and it's important that, such that gamma 1 of Y, gamma 1 of 1 should be equal to gamma 2 of 0, right? Because that is Y and that is also both are Y. They are equal. Okay? So this will be well defined. Gamma of 2t if t is in between half greater than 0, okay, and equal to gamma 2 of yeah, 2t minus 1, 2t minus 1, yeah, correct. So if 0, if it is half less than t, less than or equal to 1, that's all. This gives a path between X and Z. So this is an equivalence relation. Right. So this is an equivalence relation. Now let's make the definition for path connectedness. So definition: S contained in X is path connected if for all X, Y in S, there exists a path in S connecting X and Y. Every 2 point is path connected. That's what. S is path connected. Every 2 points is path connected in S. Okay. There is no proof. So this is the definition of path connectedness. And this is equivalent to saying you don't need to consider any 2 points. You fix 1 point and everything is connected to that point is enough. It's enough to prove this. Okay. So S is path connected if for some X naught in S, every X in S is connected to path connected to, of course, in S, to x naught. Okay, it's enough to have everything connected to some fixed x naught, because if some x is connected to x naught, y is connected to x naught, then you can take the path from x to x naught and reverse the path from x naught to, y to x naught, and you get a path from x to y. Okay, so because of this, it's enough to have this, right? This is easy exercise to see. Okay, so you have to prove that everything is connected to one single point. Okay? So all, whatever you have seen as an interval is path connected, and we will see that R and maybe. Okay, let's prove this proposition. Path connected implies connectedness. That is, X is path connected. Some S is path connected, or I just write path connected implies connectedness. Path connected implies connected. Okay. This is just direct again. We will use whatever we have proved till now. Proof. So something is path connected, some S is path connected, S contained in X is path connected. Suppose it's not connected, suppose S is not connected. We want to prove it is connected. Suppose if it's not connected, then we want to prove it's not path connected. Okay. So suppose S is not connected, then there exists U, V contained in S, such that U intersection V is not equal, is empty, and they are proper, U, V proper, open, proper open subsets, and they are disjoint, okay, such that S is equal to U. U are contained in S, okay, it's an open set, U union V. S is U union V. Okay. Now you take X in U and Y in V. Okay, because they are non-empty. So you can take that. Let gamma be a gamma from 0, 1 to S, such that gamma of X equal to X, gamma of 0 equal to X, gamma of Y equal to gamma of 1 equal to Y. Okay. Gamma of X equal, gamma of 0 is X, gamma of 1 is Y. Okay. Then gamma of this 0, 1 equal to gamma of 0, 1 is completely contained in S. So gamma of 0, 1 is gamma of 0 intersection S. This is equal to gamma of 0, 1 intersection U union gamma of 0, 1 intersection V. But this is open in gamma of 0, 1. This is when you take the intersection, that is open in gamma of 0, 1. This is open in gamma of 0, 1. This means, and this has X is here and Y is here. Okay. This implies gamma of 0, 1 is not connected. Which is contradiction, because 0, 1 is connected and gamma is a continuous function, gamma of 0, 1 should be connected, which is a contradiction. Okay. The interval 0, 1 is connected, gamma is a continuous function, so gamma of 0, 1 should be connected. We have proved that it's not actually connected. Okay. So this is not true. Okay. So path connectedness should imply connectedness. So we will see next class example where the connectedness does not imply path connectedness, but we have if it is open, then it is actually path connectedness will imply path connectedness. So we will prove that. You will see more example in the next class. So this is the proposition. This is for Rn, or this is for non-linear space. See, if you have an open ball in a non-linear space, that is path connected. Open ball is convex. Convex means any line joining them. That is, if you have x, y, okay, then the line joining them is all those points such that tx plus 1 minus ty. This is just this finite line, okay, x and y in a non-linear space. So this is the line joining them. If it's an open ball, okay, then this is contained in the open ball. Okay, if you have an open ball, if you have 2 points, if you have a center x naught, okay, you can prove this is an exercise. You can prove that this line, all these points, if you take the norm minus this x naught, okay, if norm x minus x naught is less than this norm, this x naught you can write it as tx plus 1 minus ty. Let me prove that. I mean, this is easy. In non-linear space, NLS, non-linear space, any open ball is convex. Open ball, okay, is convex. Okay, this is a convex means if you, I mean, convex, the definition makes sense only if it is a vector space or something. You need to have addition. Okay? So if you take any x and y, then that is x and y are in some ball x naught r. Okay, then tx plus 1 minus ty is also in bx naught r. Okay? As I said, you can write any tx minus plus 1 minus ty minus x naught. You can write it as tx naught plus 1 minus tx naught and use triangle inequality and you get that. Okay. So we use that to prove this. So let u contained in some x is a non-linear space. Okay. Then u contained in x is open and connected. Okay. Then it is path connected. Then u is path connected. You need the extra assumption that it is open. Then it's path connected. Proof. To prove, we assume it's open and connected. We want to prove it's path connected. To prove path connected, we choose an arbitrary point x naught in U and prove that everything can be connected to that. Okay? So let us take some E equal to all. So let's fix x naught. Okay? Some arbitrary point x naught in x. Okay? Let and E equal to all those x in U, okay, the open set, such that there exists a path in U, of course, between x and x naught. Okay? You collect all those points. Okay? We need to prove that this E is everything. That's all. Okay? So, and clearly x naught is in E. Okay? We need to prove E equal to x. That's what we want to prove. And we know x, of course, there is a path from x naught to x naught, of course. Okay, so there is no problem with that. So this is non-empty. This E is non-empty. So this implies E is not equal to empty. Okay. Now we invoke the initial implication. Because U is connected, the only subset which are both open and closed is its I mean, only non-empty subset which is both open and closed is the whole set U. Okay, now we want to prove that we need to prove that E equal to U. E equal to U, not x. E equal to U. X in this. Okay. So let us prove that. To prove that E equal to U is enough to prove. So we have noticed that it is not, E is non-empty. Okay. Now it is enough to prove E is both open and closed. Right? That's what we want to prove. So E is open. First we prove that E is proof. E is open or closed, which is easy. Open. Yeah, we are assuming that it's a non-linear space. Okay? It's not in general topology. So E is open. Okay. I mean, first claim. E is open. To prove that E is open, let X is in E. Okay. X is in E means by definition there exists a gamma, there exists a path. There exists a gamma. Okay. Between X and X naught. Okay. By writing this, there exists a path between X and X naught. Okay. Now, since U is open, okay, B there exists a R greater than 0 such that B of XR is completely contained in U. Okay. Now we want to prove that E is open. Okay. So E is open. To prove E is open, we have X in E. We have to find a R such that BXR is complete. We want to prove that this BXR is actually contained in E. Right? We want to prove E is open. To prove E is open, we want to find a R such that BXR is contained in E. But since U is open, we have a R greater than 0 such that BXR is contained in U. Now we want to prove actually this is contained in E. Okay. So to prove that, let Y is in BXR. But this is an open ball in a non-linear space, which is convex, of course. Convex means line joining them is there. Okay. So there exists a gamma prime which connects this X and Y, right? By this I mean, I just say it, okay? When I write like this means there is a path gamma prime between X and Y. Now there is a path from X and X naught, okay, by definition. So there exists a path, okay, between Y and X naught. This just means Y is in E. If what we have proved is Y is some arbitrary element of BXR that is in E. What we have actually proved is BXR is contained in E. That's what we have proved, set theoretically, right? This is the way of, if you want to prove something is contained in something, you take an arbitrary element, you prove by logic that this is an element here. That's what you have proved. Okay? So we have proved that it is open. Okay? This implies E is open. Okay? Now we want to prove it is closed. We take a sequence and do that. So within the 2 minutes, I should be able to prove the same proof. Very similar proof. Now the next claim is E is closed also. E is closed. So to prove E is closed, we take that X is in U, okay, and there exists a sequence Xn contained in E, a sequence in E, and Xn converges to X. Okay, we need to prove X is also in E. X is in E. That's all. Okay, we have a sequence in E which converges to X, which is in U, because we want to prove closeness. Everything is in U. Okay, this is a close. This need not be a closed subset in bigger one, because we are only dealing with within U. In the relative topology, it is both open and closed. That's what we are proving. Okay, so we take a X in U such that this happens. Now, since U is open, again, since we are using the fact that U is open, since U is open, there exists R greater than 0 such that BXR is completely contained in U. Okay, so there exists a Xn such that after some everything is there, but I need only one. There exists a Xn such that Xn in E, Xn is in BXR. Okay. Okay. Now there exists a gamma from gamma connecting X0 and this Xn. Okay. Now X and Xn are in this BXR. This is norm open ball in a non-linear space. Okay, and gamma 1. And gamma 2 is a line between xn and x. So there exists a path. You want to leave? No. There exists a path between x naught and x. Okay. So this implies there exists a path between x naught and x. So this implies x is in E and E is closed. That is what we wanted to prove. Okay. That's what we wanted to prove. Any question?